Hello students, Jai Hind. Welcome to my YouTube channel, and in today's lecture we will discuss the rules for the image formation in the case of lenses, and thereafter we will discuss the nature of the image obtained when an object is placed in front of a convex lens. So before we start with the ray diagrams for the image formation, we must make ourselves familiar with the rules for the image formation, right? So let's start with this session, students. So I'll state the rules both for convex as well as concave. The rules are same for both the lenses. So let's start with the first one. Let's start with the first rule. Convex lens, you all are aware, a lens which is thick at the center and thin at the edges is known as a convex lens. And as you are aware, students, it is made of two convex refracting spherical surfaces, right? And here we will be dealing with biconvex lens. Both the focal lengths are of same value, right? Both the curved surfaces are of same radius of curvature. While in the case of concave lens, you are aware it's a diverging lens and it is thin at the center while thick at the edges, right? So that's concave lens, biconcave lens. So this is the optical center. It is the point inside the lens through which if the ray passes, it remains undeviated. That also we have discussed earlier. So this is the principal axis. Suppose this is the principal axis. Now look, first rule. I have told you, you need to show the bending of light from this reference line. The lenses are considered to be very, very thin. So as a result, instead of representing refraction at both the surfaces, what we do is, just for convenience, we consider the bending of light from this reference line, isn't it? It's because of the fact that we are considering the lenses to be very, very thin. So the first rule, whenever a ray is incident parallel to the principal axis, this is the incident ray and it is parallel to the principal axis, then in the case of convex lens, it tends to pass through the focus. In the previous lecture, students, we have discussed convex lens is also known as a converging lens. So it will tend to pass through the focus. This is the focus. All the rays which are incident parallel to the principal axis on a convex lens, then the rays after refraction tend to get converged at a particular point. And this point is known as the principal focus, right? So that is the reason why convex lens is also known as a converging lens. Now, in this case, the focus is real. So if the object is placed on the left hand side, then its focus would be on the right hand side, right? In the case of concave lens, the focus is virtual. This also we have discussed. So the focus is on the same side as that of the object. So in the case of concave lens, the focus is virtual. In the case of convex lens, the focus is real. So here also the same rule applies. But here, the ray after refraction it converges. Here, it appeared to be coming from the focus. So look, this is the ray which is parallel to the principal axis. So here, after refraction, it will appear as if the refracted ray is coming from the focus. This is the actual line, right? This is the direction in which the ray will get deviated. So it will appear as if this ray is coming from a point over here. So this point is the principal focus. So student, what's the rule? Incident ray parallel to the principal axis after refraction in the case of convex lens will pass through the focus, and in the case of concave lens it will appear to be coming from the focus. It appears to be coming from the focus, it diverges. So that is the reason why concave lens is also known as a diverging lens, right? So that's rule number one. I hope it's pretty clear, right? That's rule number one. Now let's consider the second rule. Again, for both the cases we will discuss. This is the reference line and this is the optical center. This will be the principal axis. So same rule will be applicable in the case of concave lens as well, right? This is the optical center and let us consider this to be the principal axis. As I have told you, again I am repeating, if the object is placed on the left hand side, then its focus will be on the right hand side. That is, its focus is real. In the case of lenses, students, whenever the image is formed on the other side as that of the object, then the image can be always obtained on the screen, and in such a case, the image is said to be real. But on the other hand, if the image is formed on the same side as that of the object, then the image can't be obtained on the screen, obviously. So it is that case when the image is said to be virtual or imaginary, right? So this is its real focus and this is its virtual focus. So the second rule, just try to concentrate, right? Second rule is, as you are aware, there are two focus. This is also a focus. The real focus is, in the case of convex lens, the concave lens, it possesses virtual focus, right? So here the rule is, any ray, incident ray, which passes through the focus, incident ray passing through one of the focus, after refraction, it becomes parallel to the principal axis. Now students, look, it's simply the vice versa of the first rule. First rule is, incident ray parallel to the principal axis, after refraction will pass through the focus. Second rule is just the reverse of that. Incident ray passing through the focus, after refraction will become parallel to the principal axis. What I mean to say is that, suppose this is the ray. This is the ray passing through the focus. This is suppose the focus. And this is the incident ray passing through the focus. This is the incident ray. After refraction, it will become parallel to the principal axis. This is the rule I am talking about, right? Either this way, the ray passing through the focus, after refraction, it will become parallel to the principal axis, right? Over here, ray which passes through the focus will again be parallel to the principal axis. But here, how to represent this one? So it will be like this. This is the focus, right? So in this case, it will be somewhat like this. Suppose this is the ray which is passing through the focus. If it is produced, then it will be passing through the focus. But obviously here it will get refracted. So here what happens is, it will become parallel to the principal axis. This is the rule, basically, right? So again I repeat, in this case, both the rules are same. The rules are vice versa of each other, and it's applicable for both convex lens as well as for concave lens. The rule number 2 is, incident ray passing to the focus, after refraction, it becomes parallel to the principal axis, right? In this case, the incident ray which tends to pass through the focus, after refraction, it becomes parallel to the principal axis. So that's rule number 2, right? This is rule number 2. Okay, the third one and the final one. It's pretty simple. We've done it already. Again, this is a convex lens. This is the principal axis. This is suppose the optical center. This is the focus. These are the two focus, right? Let's draw the same diagram for the concave lens as well. So, this is the optical center, this is the virtual focus, right? So, the third rule is, I have told you the definition of optical center. It is a hypothetical point which lies within the cell, through which if the incident ray passes, then it won't get deviated. It will remain undeviated. So that's the third rule, like this. Look, incident ray is passing through the optical center. It will remain undeviated. It will not suffer any sort of deviation from its original path. Here also, same thing. This is the optical center through which this incident ray is passing, so it will remain undeviated. So students, these are the 3 rules which we will be making use of in drawing the image diagram in several different cases, right? So before we continue with the image formation, I must recapitulate, I must repeat all the 3 rules. So students, please listen carefully. First rule is, incident ray parallel to the principal axis, after suffering refraction it will pass through the focus in case of convex lens, and it will appear to be coming from the focus in case of concave lens. That's rule number 1. Rule number 2, vice versa of the first rule. Incident ray which passes through the focus after refraction becomes parallel to the principal axis, right? Here, incident ray which appears to be passing through the focus after refraction will become parallel to the principal axis. Clear? Third one, very simple. Incident ray passing through the optical center of the lens will not suffer any sort of deviation in its path. That is, the ray which passes through the optical center of the lens will remain undeviated. So students, these are the three basic rules for the image formation. Now let's start with the image formation. So what we will do is, we will start with the image formation in the case of convex lens, right? And students, as I have told you, real image, virtual image, the image which can be obtained on a screen, they are known as real images. While on the other hand, those images which can't be obtained on the screen are said to be virtual images, right? And in case of lenses, mind it, I am repeating it very often, again I am repeating it, in the case of lenses, if the image is formed on the other side as that of the object, like object is placed on the left hand side of the lens and its image is found on the right hand side of the lens, then the image can definitely be obtained on a screen. If you place a screen over there, then the image will be formed on the screen. So that is the real image. And if the image is found on the same side as that of the object, suppose object and image both are on the left hand side of the screen or both are on the right hand side of the screen, then obviously the image which is formed on the same side as that of the object can't be obtained on the screen, and accordingly it will be imaginary or virtual image, right? So let's start with the image formation, and we will start with concave or rather convex lens image formation in case of convex lens. So there are 6 cases which we will discuss turn by turn. So let's start with the first case. Let's start with case number 1, right? When the object is at infinity, right? When object is at infinity, means the rays coming from the object will be considered to be parallel to the principal axis, right? So let's check it out. This is a lens, and students, remember, the lens are considered to be very, very thin, so always remember that. So this is the optical center, this will be the principal axis, and it's a bi-convex lens. It has got 2 focus, both of equal focal length. So this should be the same distance, and this is the reference point, 2f. So twice the distance of the focal length, right? If this is small f, this is twice into small f. It is just a reference point, f to f. And don't get confused between radius of curvature and the focal length. The relation small f equals to r by 2, that's not valid in the case of lenses. That is valid only in the case of mirrors. So here there is no such relationship, right? So if this is 5 centimeter, this would be 10 centimeter. So all these distances should be equidistant. Then only you will be able to draw appropriate ray diagram, right? So this is the reference line from where the refraction light will be indicated. So the rays are coming from infinity and all are parallel. So if the object is at infinity, then the rays will be parallel to each other and will also be parallel to the principal axis. Now, as you are aware, after refraction, all these rays tend to get converged at a particular point, and that particular point is known as the focus, right? So this is where the image will be formed. So students, whenever the object is at infinity, then the rays from the object at infinity would be parallel to each other and also will be parallel to the principal axis. So because of its converging nature, all these rays after refraction tend to get converged at the focus, right? So what about the nature of the image? First, object lies on the left hand side, image is found on the right hand side at the focus. So it is real. If you place a screen over here, a point size image of the object will be obtained, right? So image is real. write inverted because it is point in size. Images point in size. Images point in size. Third situation, third property. Image is formed at the focus. Image is formed at the focus. Right? It is exactly formed at the focus. What about linear magnification? Since it is point in size, therefore linear magnification is 0. Remember students, linear magnification, we have discussed it in the case of mirrors as well. It is defined as the ratio of size of the image to the size of the object. To the size of the object. So since the image is point in size, therefore linear magnification in this case is 0. Right? So this is case 1. So image is real, image is point in size, image is formed at the focus, and linear magnification is 0. Right? Now let's consider the second case. When the object is at a very far away distance, not at infinity, but at a very, very far away distance, right? So, this is the convex lens, this is the optical center, this is the reference line, and this is the principal axis. This is F, this is 2F, this is F, this is 2F. Students, please take care while indicating F to F. All should be equidistant. Please ensure this, right? Now, basic difference between these two. It is the case when the object is at infinity. So, all the rays are parallel to each other as well as they are parallel to the principal axis. In this case, the object is at a very far distance. So, therefore, rays coming from the object will be parallel to each other, but not necessarily parallel to the principal axis. So, what I mean to say is that in this case, the diagram would be somewhat like this. These are the rays which are parallel to each other but not parallel to the principal axis, right? So here the rays will again get converged at the focus, but here the image will have some finite dimensions. So what happens is, it will be like this. It will get refracted and here the image will be formed like this. This is suppose A dash, this is suppose B dash. So students, the point I am making is, the rays which are coming from an object which is at a far away distance, not at infinity, they must be parallel to each other but not necessarily parallel to the principal axis. In such a case, the image is again formed at the focus, but here the image is not point in size. It has got some finite dimensions. So in this case, the nature of the image is real, and since it has got some finite dimensions, it is inverted. Real and inverted. Second, it is formed at the focus. Third, obviously, image is very small, diminished in size. Image is diminished in size. That is, linear magnification is less than 1. Mod of n. We are not using any sign convention over here. Just in magnitude, linear magnification less than 1. It indicates the size of the image would be less than that of the size of the object. So, got the difference between these two. In both the cases, the image will be formed at the focus. But at infinity, the image is point in size. While when the object is at a very, very far away distance, then the image is having some finite size. And look, if a screen is placed over here like this, if I place a screen over here, a cardboard or whatever, a chart that can act as a screen. So if I place a screen over here, then this small inverted image of that distant object can be easily obtained. So what I mean to say is that object over here lies on the left hand side, its image is found on the right hand side. Therefore the image can be obtained on the screen, and accordingly this is the real image. Clear? So we have discussed two cases. Now what we do is, the object is brought still closer. The object is brought still closer. So gradually the object is brought closer and closer towards the convex lens. So case 3 will be when the object is placed beyond 2f, beyond 2f. So let's discuss third case. Object placed beyond 2f. Object is placed beyond 2f. So diagram would be like this. Lens should be thin. This is the optical center, it is the principal axis, and as I mentioned, please ensure these are the equal distances. These are the equal distances. If you consider it to be 3 cm, it will be 3 cm, it will be 3 cm, it will be also 3 cm. It is only then the ray diagram would be exact and perfect, right? So here the object is placed. Suppose here the object is placed. This is A and this is B, and this is the reference line. And this is the object which is placed, right? An erect object is placed, and it is placed just beyond 2f. So this is case 3. So let's make use of the rules, student. There are 3 rules as stated. First rule is, any 2 rules can be used, isn't it? First rule is incident ray, which is parallel to the principal axis. After refraction, it will pass through the focus. It will pass through the focus. Is it clear, students? Incident ray parallel to the principal axis, after refraction, in the case of convex lens, will pass through the focus. This is rule 1. Let's make use of rule 3. Rule 3 was a ray passing the optical center of the lens will remain undeviated. This is the optical center, right? So it will remain undeviated. So here the intersection of the refracted rays is obtained. So here the image is formed. So if the object is like this, the image is inverted. The inverted image is obtained. So this will be A dash, this will be B dash, right? In case, students, in case you make use of the second rule, then also at the same position image will have been formed, right? It will be like this. The ray which is passing to the focus, after refraction it will become parallel to the principal axis. So you should have got the same point of concurrency. So out of 3 rules, it's your wish, students, to make use of any 2 rules so as to get the position of the image, right? So here I have used 2 rules, which are ray parallel to the principal axis after refraction passes through the focus. Second is ray which passes through the optical center remain undeviated. So this is where the image is obtained. So let's find its nature. First, look, it's pretty clear. Image is formed on the other side as that of the object. So image is real. And it's pretty evident from the diagram, it is inverted. Image is real and inverted. What's the second point? Image is formed between F and 2F. Image is formed between F and 2F. Third, look, the size of the image is less than the size of the object. That is, H2 is less than H1. Or H2 by H1 is less than 1. That is, ratio of the size of the image to the size of the object. H2 students are considered it to be the size of the image. H1 is considered to be the size of the object. So ratio of these two is less than 1. That is, linear magnification is less than 1. That is, the image of the size is small or diminished image is obtained. Diminished image. So these are the properties associated with the image in this particular case, right? So what we are doing here is, we are gradually bringing the object closer towards the convex lens. So far we have discussed 3 cases. Object at infinity, object at very large distance, object beyond 2f. Now students, let's discuss case 4. Yeah, case 4. The object is brought still closer. So let's see what will be the nature of the image and its position when the object is placed at 2f. So here we will discuss when the object is placed at 2f. So let's try to draw the diagram. This is a convex lens which should be thin. This is the principal axis, and again it's a reminder, student, please pay attention. This f, this is 2f, it should be equidistant. If you consider it to be 5 centimeter, then it should be also 5 centimeter. It should be also 5 centimeter, and this should be also 5 centimeter, 2f, right? So that the distance from the optical center, it will become twice, 2f means 10. So keep this in mind. These points are absolutely necessary so as to draw the ray diagram. These are the reference points, right? You should draw it most appropriately. Now, as per our objective, the object is placed at 2f, like this. This is A, this is B. And this is the reference line through which the bending of light will be shown. Let's make use of the same rules which we are using. Ray parallel to the principal axis. It is the incident ray coming from the object and is parallel to the principal axis. After refraction, it will tend to pass through the focus, like this. It will tend to pass through the focus. It's clear, student? This is rule number 1. And what about the second rule? A ray passing the optical center, a ray passing through the optical center will remain undeviated. A ray passing through the optical center will remain undeviated. It's like this. This is the ray from the object which is passing through the optical center, and it will remain undeviated. So these two refracted rays meet at this point. So if you draw the ray diagram correctly, you should get the image to be formed exactly at 2f. This is 2f. So this is A dash and this is B dash. If this is the object, students, if this is the object, then its image will be formed like this. Inverted image will be formed. And the size of the object is found to be exactly equal to the size of the image. We will justify this mathematically as well by using lens formula. That we will discuss later on, right? So remember, students, in case the object is placed at 2f, then its real, inverted and same size image will be also formed exactly on the other side and at 2f, right? This is a very, very important situation. So what's the nature of the image then? Image is real and inverted. Image is real and inverted. What about the second case? Image is formed at 2f, exactly at 2f. Third, here size of the image, which is denoted by h2, is equal to h1. Therefore, m, which is equal to h2 by h1, is equal to 1. The linear magnification is 1, and mod. If we use sign convention, then m would be equal to -1. That also we will discuss later on, right? But in mod, in magnitude, the linear magnification is equal to 1. That is, the image is of the same side as that of the object. Here I must tell you, if you would have made use of the third rule, then also you would have got the image at the same position. I'll tell you. So one of the rules left was ray passing through the focus. Ray passing through the focus. After refraction, it will become parallel to the principal axis. So you will get the same point of concurrency. So this is the rule. Ray of light passing through the focus. After refraction, it becomes parallel to the principal axis. It will become parallel to the principal axis. So students, what I mean to say is that out of these three rules, make use of any two rules. Make use of any two rules. You need not to make use of all the three rules so as to obtain the position of the image. Just make use of any two rules, right? So we have discussed 4 cases. What's the common point in all the 4 cases? So far, the nature of the image obtained is real, right? In all the 4 cases which we have discussed so far, the nature of the image obtained is real. So students, we will discuss the other cases in the next session. So please practice all these ray diagrams, right? All the very